Greetings. In this video, I am going to discuss wood cost estimating or doing quantity takeoffs for wood framing. Not so much the cost part of it, but really just counting all of the wood members that make up a structural frame. So we will talk about the terms, the different materials, measurements, and reading construction drawings, and the formulas for figuring out just how much material is needed. And we'll look at some examples. So just briefly about framing. Wood framing has evolved over the years. From the early days, previous to balloon framing, it was heavy timber framing, really. Heavy timbers that were cut down really on the farm in the exact area pretty much where the building was built. That's how it all started. And then about 1830 or so is actually when the railroads started making their way across the country, the United States. And that is when dimensional lumber from sawmills became available throughout the United States. So originally there was the balloon framing, 1830 to about 1930, the first 100 years. Timbers were long, and they extended from the ground floor up to the second floor. So this is a long, continuous timber. So that wasn't the most economical, and a big problem it caused was that fires in the walls were able to run up past from the first floor to the second. So for economics and other reasons, it became platform framing, which is what we have today. And that is, we build walls to the first floor, and then we stop with joists, plywood, so that if a fire were in the wall cavity, it would stop right here, or at least be slowed down. And then we build again on top of that, and then repeat, rather than building long two-story walls. So here's a contemporary picture of a wall going up. So balloon framing is used sometimes in contemporary buildings when there are two-story spaces, perhaps. But again, accessing dimensional lumber that's beyond 16 feet is it gets expensive. So it's not too common. Okay. So here's an image of a typical large but typical platform framed building, and we can see right here that is the second story floor cutting right through the middle. This looks like it was built slab on grade. I can't see a basement from this vantage point. Okay, so let's look at the parts that make up a floor. I have numerous illustrations that we'll look at. Some are three-dimensional. Some are kind of more like artist renderings, and some are actual construction documents. So here is our floor. We have a foundation, could be a crawl space, could be a full-on basement, doesn't really matter, doesn't really change the framing here. And so there is a beam cutting through the girder. Actually, we'll call it a girder. Girder is the typical term that's most common. So we have a girder cutting right through the middle there, and then the joists, the floor joists. Well, actually, the very first piece to go down. Let me do this in order. The very first piece to go down is the sill right there that sits on the concrete, and that would be a pressure-treated sill, and that runs all the way around the top of the concrete wall, and it is bolted. There's a little bolt I think we can see right there. And in this picture, this is an odd detail that I chose. There's some sort of a pressure-treated wall underneath, but we'll just pretend that that's concrete. And then right up here, so they're calling them top plates, but actually if this were a concrete wall, that would be a single sill right there rather than a double top plate. But building pressure-treated walls under the earth is really uncommon. But same difference, really. If this were concrete, there'd just be a single plate there, and then the joists come, and that's what we have right here. So sill being wrapped, joists extending from the load-bearing. This is a load-bearing foundation wall. Same on the back, load-bearing. This would not be considered a load-bearing wall. Perhaps carrying some weight, but not. But as you can see, the great majority of, or really none of the joists are resting on it. This end rim board here is. So this is a load-bearing wall girder in the middle, and then the joists bridge from the girder over to and sit on the pressure treated sill. All right. Then we have, this is called the header joist or a rim joist. There's a lot of different terminology, and it's very regional. Different parts of the country just have different terms for the same pieces. So if you're Googling things or reading books or articles, you'll probably come across the same name, especially in framing. I find that in wood framing in particular, of all the different building trades, wood framing I find the most diversity in terminology. So header joist, sure, we could call it that. I think I mostly know that as a rim board. But basically the joists have to come, and right here is where the plywood, the sheathing on the outside of the building, has to start coming up. So we need to cap these, and so we'll face nail through that board, through that header joist, into the joists. Okay, we have blocking here over the girder in between the joists. They didn't draw it there, probably just for clarity, but that's what that is. We'll see a lot more on that. Solid blocking coming in. That keeps the joists from wanting to lean over and kind of twist. And that's all that would be below there. So, yes. And then the subflooring comes next. This is not drawn proportionally at all. 4x8 sheets of plywood, that's not drawn well. All right, and then here we'll pretend we have our foundation, pressure treated sill, joists right there. That would be our rim board or header joist. And when we look at these details and we see a rectangle with an X through it, like we see right there and there, that means it's a continuous board. Same with that one. And I don't know what this is. I should really get rid of this detail. It's really kind of goofy, like that square block. That's not what it looks like typically. But we'll see other better examples coming up. Okay, and then the joists run that way. All right, so again, this is not a construction document, but it's more of an illustration of the different parts. So we can't see the foundation wall, which would be here. The load-bearing portion, the load-bearing wall would be here and here, and here's a girder coming right down the middle, and this, I would call this a triple built-up girder. So it's made up of 3 different boards, and they are nailed or bolted together. And then we see the joists extending from foundation wall to girder. We see the bridging or blocking, 2 different terms there, bridging or blocking. Typically mid-span, they'll put it over the girder at the end of the joist, and they'll also put it mid-span. And there are many other pieces involved in openings, or not many. I mean, they're also a lot of the terminology in openings in the floor are also used for openings in walls. So trimmer joists, or just trimmers at least, you'll see that when it comes to windows as well. I'm not going to go into the detail here. I just want to kind of stay focused on the bigger picture right now. So whenever there's an opening, there are more parts that have to come around. Obviously, if there's a chimney coming up or a stairwell, we need to accommodate that, and we double up headers, but we're not going to really get into that in this particular lecture. So this is more what a construction document would look like, and even this you wouldn't really. Often in residential work, it's really incorporated into architectural plans, but this looks like a standalone structural drawing actually. So I can't see a lot of this here. I see foundation wall here. So these single lines, these are the joists. And yeah, so they're typically not depicted they're never depicted in construction documents as double lines. They're single lines. And we are probably, I'm not exactly sure what level we are on, but here we are pointing out that there are headers above windows. So it's telling us exactly what the sizes of those are and how many there are. So here, around the stairwell, again, the specifics. This this corner of this plan is not the clearest to me either. So, but in general, just visually, this is more what you would expect to see in a construction document. Okay, I'm going to keep moving along. Here's a nice three-dimensional view of what's happening. So we have, again, I'm not exact. Oh, so we do have, it looks like studs, platform framing down below there. I can see studs in the back. So these are load-bearing walls. And here's a steel joist coming in, very oddly placed above a large opening. That's very peculiar. I'm not sure that that would actually occur like that. But then we see joists extending. It appears to be a single joist running all the way over, so this is all kind of suspect in my mind. But nonetheless, it provides a good three-dimensional view of kind of what things might look like, with some little things that are peculiar about it, I would say. But joists going from an outside wall to an interior load-bearing wall. So in this exercise, it's definitely important to understand the difference between load-bearing walls, exterior ones, and interior ones. So there are 4 here. 1, 2, 3, 4. Those are carrying the loads up from the roof. The snow on the roof has to make its way down, and it's going to make its way through these joists, and then the loads will make their way down these walls. There are other partitions inside, inevitably, that will not be carrying such load, like this partition that we could see through there. That partition runs parallel to the joist, so that would not be a load-bearing wall, just like this one, running parallel to the joist, not load-bearing. All right, so one more. So this is a nice clear example. Concrete foundation below, girder, joists. Easy. Girders could be built up and composed of dimensional lumber, or they could be engineered. So these are kind of look like some vintage diagrams. So here we see a steel beam as the girder, wood plate on top of it, joists coming from each side of the foundation and crossing past one another. So you wouldn't make joists just meet and butt into each other. They would cross over each other and overlap some, and then we see the blocking coming in. This is pretty common. This is a pretty common one. I've seen this one in person and in design. This complex one I've never seen in my life. But this just goes to say that, over time and different regions, different details are created. So I'm not saying there's anything wrong with it necessarily. I haven't come across it myself. So we have a built-up girder that's been separated with blocking for some reason. Joists coming in that are ledged. That's common. I've seen that in older buildings. That's what we see here too. Here we see the girder, ledges on the bottom side of each girder. Now we use metal joist hangers, but vintage details and older houses, you'll see ledges down there. And then the joist will come and sit on the ledge. Notching a joist like that, again, a lot of work and not common. Definitely not these days. You'd avoid that. Between the labor and creating a weakness in the joist, there's really no reason for that these days. So this is the most common of this group. And here, this is really what it would look like today. So large engineered lumber. I mean, that's what we see here. So here we see something that's built up. So we would call this a triple. It's a little fuzzy. I don't know what that says there in terms of dimensions, but 2 by 10s, 2 by 12s would probably 2 by 10s would probably be most common, built up like this, and they would break on top of columns. That's where the seams would be. But this is pretty much what it looks like most of the time. Large girder, and the joists tie into it. These joists, the top of this joist is flush with the top of this girder, and that provides the most headroom down here. So if you've been in old houses, sometimes when we come back to here, for instance, not this detail. So these details aren't so bad, but this detail, for instance, the steel beam is dropped below the joists. this is the quickest and easiest one to construct, but as far as headroom in the basement, if it's an older house, you're probably stooping down so you don't bump your head on that steel beam, which is very common in old houses. So in order to get livable space and to provide now what's a code compliant ceiling height, the joists are moved up and the top of the joist is flush with the top of the girder. And okay, so now we're looking at an example from the D'Agostino textbook. Great book, and I'm not going to go into detail here so much about. Well, I might discuss the formulas as we go. Let's see how it goes. So here's a basic floor plan. Foundation wall around the outside, a triple 2x10 girder coming across the entire way. It is breaking probably on these columns or piers. So we have 1, 2, 3, 4, 5 10-foot segments that make up this girder. And these are called bays. So the space in between the term bay is used in many different ways in architecture and construction, but here a bay would be the space between the outside wall and here. So that's 1 bay, 2 bays, 3 bays, 4 bays, 5 bays. So we have 5 10-foot bays equate to 50 feet, and we have 12-foot spans from the outside wall to the interior girder. Okay. So the question is, how many joists do we need to buy? And that, of course, depends on the spacing, and that tells us right here that these joists are 16 inches on center. OC is on center. And the text here will take you to the figures and the pages where this is in the D'Agostino textbook. These are some of the drawings from the textbook, which are decent. Some of them leave a little bit to be desired. So here we have a foundation wall that is built up of concrete masonry units. We have a girder that is sitting on top, so it's been notched. That's a good example right there. So the masons have made way for this girder to sit inside the wall. It comes over. The top of the girder sits flush with the top of the concrete here. Here, the top of the girder sits flush with the sill. It appears like there's another middle board right there. So the joists that we see here, 1, 2, 3, are resting on another dimensional piece of lumber that is sitting on top of the girder. I think we saw something like that in that steel detail one more time. Where did that go? Right here, right? Girder with plate on top of it. And that's what we just saw there. Girder with plate on top of it, so the plate and the sill match, and then the joists all work that way. So this was cut in one direction where we actually cut through the joists, and this one we're seeing the joists long ways, and we've cut through the girder. So if I come back to this floor plan, which he didn't tell us exactly where those cuts were made, but one cut would be made in this direction, where we could see into the joists, and then another cut was made in this direction, parallel to the joist. So we can't see all the joists end, but we're running parallel to the joist. So when we run parallel to a joist, we just see the face of it. When we cut perpendicular, when we cut a section perpendicular to the joists, we see the joists with the X's. That means we've cut through it. So if we cut through right here, we would see that X right there. Okay, so yes, let's talk about the calculations. So here's a girder that is figuring out the amount of lumber needed in this girder. So we have a 50-foot span right there, okay? And what he is trying to calculate here is the total length of this girder. So is it 50 feet? Again, as we recall, dimensions that are given on plans are from the outside wall, the outside of the foundation wall. Okay, so when we zoom in here, we can see right there that this 50-foot dimension takes us to the outside of the concrete and the outside of the concrete. Okay, so the girder is not actually 50 feet long in total. So that's why right here he's subtracting the 8 inches from each side. So this must be a, I'm not sure why it's a full 8 he's subtracting, but if that's an 8-inch block, he's subtracted some portion of it. The overall result here is kind of negligible. It's not really so important. I don't think this calculation really changes it, but so the 50-foot girder becomes 48 2/3 feet, basically. So we're taking the girder length and we're figuring out, and that's called the bearing distance. So that's an important part of the discussion right there. That area right there, the girder is sitting on the wall. That is the bearing distance. Okay, so that 8 inches he's subtracting. It doesn't really change the outcome, but you should be aware of it because it could change the outcome in some scenarios. When he's using numbers like this, not really. So in short, let's see. So this is a, what did we say? This is a triple girder or a double girder? 3 2x10s. 3 2x10s make up this. So the calculations tell us that it's basically 1, 2, 3, 4, 5 2x10s to reach across here. It's a triple girder, so the 5 times the 3 gives us the 15. It's, in this example, it's really that simple. He goes through it in a little more detail, but like I said, this little reduction in girder size is not going to change what you're buying in this particular example. Okay, so that is the conclusion here, is that the girder 2x10s, they are 10-foot lengths, and we are buying 15 of them. Okay, and that will get us across there. All right, and we'll look at another example. I'm going to keep moving through this pretty quickly, but we will look at another example. Okay, so then we have our girder in place, and now the sill comes. So sills, length of the sill plate required is the distance around the perimeter of the building, basically. All right, so there are different sills. There are sills that are in contact with the foundation. That is this sill here, okay? And this is another goofy detail. This is another goofy detail here, okay? Why are these studs coming down past these joists? That's odd. All right, so disregard that. What we're talking about right here is this sill plate sitting on the concrete, and that's on a foundation wall. Even if there's not a foundation wall and it's a slab, we still have a sill plate. All right, so they come in different varieties. So this green one is a pressure treated one. Anything in contact with concrete should be pressure treated. So we have one, so we'll circle the whole building once with pressure treated, and then we'll have a just a standard dimensional sill on top of it. Okay. All right, so here we come to our example. Yeah, this is very strange. Again, not the best example that I picked, that these studs reach down past the floor. That's very uncommon. I don't know what that means. But anyway, let us look at the sill. So I don't have his calculations, but it's pretty easy to figure out that we need to get around this building, and the sill plate is sitting on top of the foundation wall. 50 feet plus 24 feet plus 50 feet plus 24 feet. And that would provide this sill plate. And yes, there is sill here, even if the joists aren't resting on it. The end joists have to rest on it. So just to keep the dimensions, the heights straight, we would have sill plate everywhere. So 50 plus 50 is 100. 24 plus 24 is 48. So we need 148 linear feet of sill plate. 148. So let me just quickly bring up a calculator just so we could see these numbers. So now you could see my calculator. And we just said it was 50 plus 50, 24 plus 24 for a grand total of 148 linear feet of sill plate. Then the question is, what do we want to buy? So we could buy, it's typically most economical to buy the largest pieces. So we could divide this by 16-foot pieces, and we would need 9 1/4 pieces. That tells us that 3/4 of a 16-foot piece is wasted. And that might be acceptable. If it becomes too big of a number, or you could get so specific that you have no waste, but some waste makes sense. You don't want to just pick it. You don't want to get it so accurate that there's no leeway in it. Some waste, especially since we're not if we're not going to go to the extent and say, one simple way to do this would be to divide the 50. If we wanted to, we could also just say that we're going to buy 5 10-footers and get across here. That's a lot of work. That's 5 boards rather than, say, if we bought 3 16s, right? If we just bring up our calculator quickly, if we said 16 feet times 3, no, so that doesn't do it. Okay, so 16-footers are kind of awkward in there. To get to 50 feet, 50 feet's kind of an odd number. So 10-footers might actually be the best. But there would still be waste, of course, over here. If you wanted to do it most accurately, you could say 5 10-footers, 5 more 10-footers, 2 12-footers, and 2 12-footers. And that's provided no waste. So as long as there are no mistakes made, that's acceptable. No mistakes on the carpenter's part. You're basically telling your carpenters, we got only what you need. Otherwise, if we bought 16-footers and we had 3 of them, that would take us 48 of these feet. Carpenters in the field would figure this out and probably not just add on a little 2-foot piece. They would do the math and come up with bigger, better pieces. You don't want to just add on tiny little 1 and 2-foot pieces when you get to the end. That's poorly planned. So perhaps for this, and you could open up the D'Agostino book and see what his solution was. It might be 5 10-footers, 5 more 10-footers, 2 12s, and 2 12s. For this particular example, that might be the best solution, actually. All right, so then we have our sill plates in place, and then we want to add our joists. Okay, and they will sit on the sill plates. And this detail looks better. This looks like it was from the same nogging. I've never heard that word in my life. I don't know. Maybe this is European or something. I don't know what. I've never heard that one. So there's our sill. Our joists are coming over and sitting on it nicely. There's our rim board or band board or joist header. The boarded floor, we would call that a subfloor. This might be, I don't know where this is from. Subfloor or floor or sheathing. Floor sheathing is also common. And then this sill plate, this is the one thing I don't like about this detail. This subfloor would be underneath that sill plate. All right, so that's another red flag for this detail. And then we could see some joists happening there as well. So not too much to describe there. Okay, so more images of joists tying into a beam here. Joists sitting on top of a girder with blocking. Joists reaching a girder mid-span. Rim board. So these are I-joists. Oh, so this was the point of this, actually. These are the different varieties, different types of floor joists. That was the point of this slide. So dimensional lumber, what we typically buy at the Home Depot. So 2x10s, 2x12s. Very common. Also common are I-joists. Okay, so these are, they kind of mimic steel I-beams. So they have top flanges and bottom flanges, and then they have a web. Very sustainable, basically. The webs are made up of cutoffs, basically wood scraps that have been glued together, essentially, creating a very efficient, not much waste, no waste. It's structurally designed it's provided with only the wood that it's needed to do the job that it has to structurally. And just like steel I-beams, they cut out all that additional steel that they don't need. There's a lot of wood that's not needed. So in a wood beam, there's in a wood joist, there's a lot of extra wood here in the middle of the body that's really not needed structurally. So this is very efficient, and they're very light as well. Probably one carpenter could carry this entire joist. Could be a little unwieldy maybe, but they're surprisingly light. And wood trusses, also very popular. This wood trusses allow for wiring, and if they're deep enough and big enough, they could allow for HVAC, ductwork to run through. Pipes could definitely run through. So it provides a plenum in a, if we're in a finished basement and we have to run utilities, mechanical things above the ceiling here, this is the best option really, because we don't want to generally, there are rules and regulations to cutting into solid pieces. These things you would typically never cut. Sometimes they come with punch-out panels, but you would never cut these things besides cutting them to length. So trusses provide an opportunity for running things through them. All right, we saw this detail, and I have nothing else to say about that. So here, here's the I-joist cut in section. Here's a rim board. So you typically would not put I-joists at the end because they don't provide for good nailing surfaces for what's coming on the outside. Here are trusses cut in section. We could see the top and the bottom chords. So here's a truss, that's a chord. I think it's the same as here, right? No, here they're called flanges. And here they're called chords. That's a chord, top chord, bottom chord. And that's what we see cut right there. Top chord, bottom chord. So trusses in section, I-beam, I-joist in section. All right, how to calculate the number of joists that are needed. All right, the length of the floor is divided by the joist spacing. Round decimal up to get whole spacing, and then add one joist. Okay, so the length of the floor is divided by the joist spacing. So let's just flip forward. So here is the length of the floor, 50 feet. And we are going to divide it by the spacing, which is 16 inches on center. So very simply, if these joists were 1 foot apart, there'd be 50 of them, plus one. Okay, we need one at the end. We need one at each end. So if they were 12 feet apart, 12 inches apart, 50 divided by 1 foot gives us 50. Plus 1 is 51. If they are 16 inches apart, what's the math on that? Well, the math is, here's the spacing, 16-inch spacing. We're either going to divide that length by 1.33 or multiply that length by 0.75. Okay, so let's bring up that calculator. And if we have 50 feet and they are 16 inches on center, right here, 16 inches on center. Let's multiply it by 0.75. So this is going to give us a number that is less than 50. Less than 50, right? Let's just see where we go. Times 0.75 equals 37.5. We'll say 38. 38 joists. Plus 1 is 39, all right? And the logic, right, the spaces get bigger, we have fewer pieces. So as the spaces get bigger, these numbers are going to produce a smaller number of joists. So typical spacing for residential is 16. In certain applications, you'll see 12 or 24. So if these things were 24 inches on center, we would simply multiply it by 0.5. So we would have 50 feet times 0.5, and not surprisingly, there are 25 joists then, right? So if we come here, 50 feet across, if they were 1 foot apart, there'd be 50 plus 1. If they were 2 feet apart, there'd be 25 plus 1. If they were 16 inches apart, 50 times 0.75, there would be 38 plus 1. All right, so 39 is the answer to the question. It takes 39 joists to get across this space. And these joists only reach to here. So it's 39 up here and 39 down here. So that tells us, or that gives us, I closed my calculator, 39 times 2 is 78 joists. Okay? Let's just see what else. Number of joists, yes. Joist length, so 12-foot lengths. All right, so that's 78 12-footers. And yes, you would break them out by various sizes. This is obviously just a simple rectangle, so there's nothing more to it there. Okay. Let us move on to sheathing. Let's look at sheathing actually. Okay, so we have our joists in place, and now we have to cover this in plywood. Okay, and that's what we see happening here. Joists have been set, and now we have plywood coming on top. So a sheet of plywood is 8 feet by 4 feet. 8 feet by 4 feet, or 32 square feet. Okay, and here's just some other, these are some diagrams. So a computer program would do this for you, or you could draw it yourself. And we're just going to do it by square foot. We're just going to do the math. But what this shows us, and this is what carpenters would think about in the field, the most efficient way to do this by not wasting material. When the plywood, so this is a 4x8 sheet of plywood right there, when this is getting laid down, these seams, or joint, or yeah, seam, I would call that a seam, this seam can't be in line with that seam. So the seams have to be staggered over to here, so that is staggering the seams. So that is why the carpenters decided to start here with a 4-foot piece. They would take a sheet of plywood, cut it in half, put a 4x4 sheet right there, and then start running it. They put the 8-foot sheets down, and then whatever remains, some odd piece remains there. Then they would start with an 8-foot sheet, and the seams would be staggered, get down to the end, and then they have again some odd piece down the end. Okay, so this is one version, and then just quickly come here, and then they're saying, in whatever, I guess this is advertising some computer program or something, snap on this corner down here, put a full sheet down there, and how does it change it? Does it change it? So we start there, we get some odd pieces down here at the end. If we start down at this corner, does it change it? I don't know the answer to the question for this example, but kind of the moral of the story is the most efficient way to do this is to draw it and to work it out. That could be done for a simple building like this. You could just do a simple hand sketch. You know, more complicated buildings, this I think might be the same piece, right? This looks like the same actual project. More complicated buildings would require some computer drawing, perhaps, to do it more efficiently. But this is the most efficient way to do it, to figure out the geometry of how it's going to work. The easy way to do it is to simply do the math. So let's just go back here and do the math. Okay, so I'm going to clear my calculator, And our building example here is 50 feet by 24 feet. So now we are doing square footage, okay? Everything else we are really kind of doing in linear feet. Now we're doing square feet for plywood. So 50 times 24 will give us the square foot area of this project, of this floor. So 50 feet times 24 feet gives us 1,200 square feet. That is the size of this floor. A sheet of plywood is 8 by 4 feet, or 32 square feet. So how many sheets of plywood? We would divide this by 32, and we need 38 sheets of plywood. Now, again, that example we just looked at showed that there could be quite a bit of waste. So the prudent way to do this would not be to buy 38 sheets of plywood. Again, we could kind of, it probably would work actually. I think 38 would work here because this is 24 feet, which is divisible by 4. Let me see if I could actually just draw a little shape real quickly here. So our sheet of plywood, I'm not drawing this to scale. I could, but I'm not. That would be our sheet of plywood. And it's 4 feet tall. And being that this is 24 feet, it's going to be, I could just do Control C, Control V. So this is pretty good to scale, actually. Not really, not really. So that's not, so my pieces are not drawn to scale because this is a 4-foot edge, 4 foot, 4 foot. So it would take 3 pieces of plywood to run there. It would take 6 pieces of plywood to get all the way across this thing. Right? In 8 feet going in this direction, however, 50 is not divisible by 8. So we would have 8, 16, 24, 32, 8, 16, 24, 32, 40, 48, and then we're going to have 2 extra feet down the end. The carpenters again would have to do some calculations to figure this out. But the moral of the story is, if this is 38, I would probably buy, I don't say it would be as much as 10%. It depends on the complexity of the building. A very complex building, I'd say maybe a 10% addition, something like this, I would add 5%, or, just a few sheets. So if we're saying 38, so let's just clear this and just out of curiosity. If we had 38 sheets and we wanted to figure out what 5% of that is, we multiply it by 0.05, and we'd buy 2 extra sheets. I think that's a good number. For a rectangular building, 5% of waste, so I would buy 40 sheets, and I'm pretty confident that that would work with this building. Again, getting into crazy houses that have lots of jogs and different odd shapes, it would be much more complicated, obviously.